So in our last lesson, we continued our investigation of the Gaussian integers and extended several notions that we are familiar from the integers over to the Gaussian integers. Specifically, we saw how to define what it means for a Gaussian integer to divide another. We also saw what it meant to be prime over the Gaussian integer and when two Gaussian integers are relatively prime. Today, we are going to go ahead and continue that trend and prove a division theorem for the Gaussian integers. But we are not going to stop there. We are also going to prove an analog of Bézout's lemma for the Gaussian integers. We're going to talk about the Euclidean algorithm for the Gaussian integers. And we are going to conclude by investigating linear Diophantine equations for the Gaussian integers. And what we will see is that each of these results that we cover, the proofs are essentially analogous to those done over the integers, except that now we're working with the Gaussian integers. And so anytime that we use the Wall ordering principle over the integers, now we will apply the Wall ordering principle, but to the set of norms of the Gaussian integers that we are considering. And so we're going to be seeing this technique be used repeatedly today. As with our definitions over in our last lesson for the Gaussian integers, there are some things that don't hold verbatim over the Gaussian integers as they do for the integers, and that will be one of those will be the notion of what it means to have a greatest common divisor. Over the integers, we take for granted that there is a greatest common divisor, and it is the greatest common divisor in the sense that it's unique, because we define it in terms of the ordering of the integers. But now, over the Gaussian integers, that ordering is not there. And so what we will have is that the greatest common divisor is unique up to unit. And so whenever we say this phrase, up to unit, it says that our greatest common divisor will differ from another possible greatest common divisor by multiplying by a unit. So if we have G, and there's another greatest common divisor D, then there's a unit such that G is equal to D times U. And so when we get there, I'll go ahead and re-emphasize this. But this is just to motivate the ideas that we will be discussing in today's lesson. So let's first start with proving a result that will lead us in the direction of proving the division theorem for the Gaussian integers. And that is the following. If we have two Gaussian integers, a and b, with b not equal to 0, and we consider the ratio, which is a over b, and we're going to call that z, then we can find some Gaussian integer in z adjoint I such that the modulus of z minus q is at most root 2 over 2. Now this result can be proven quite easily in terms of geometry, and that's how the book proceeds to do these arguments. And I highly encourage reading this section in the text, since the way that I will be doing the division theorem is algebraic. But these ideas do allow extension towards arbitrary rings that are, in the language of abstract algebra, Euclidean domains. Whereas the way that the geometric proof is presented does depend on properties of the Gaussian integers. And so the first result that we are going to do is this one here, and the reason why this should come to no surprise is that whenever we take a ratio a over b, that's going to be a complex number. So it's going to be in the complex plane. And so here's our complex plane. This is our imaginary axis. This is our real axis. Anytime that we have some complex point z, so let's say that z is over here, it's always going to be within a square whose vertices are Gaussian integers. And so every grid point here is a Gaussian integer. So here's I, here will be 1 plus I, 2 plus I, 3 plus I, 3 plus 2i, 3 plus 3i, so on and so forth. And so we can see that the greatest distance that we can ever be inside this square is the center of the square. But to find the center of the square, since this side here is length 1, and this one here is also length 1, so we have a square of area 1, the diagonal is going to have length radical 2. So half the distance is going to be radical 2 over 2. And so that's going to be the greatest distance that our point can ever be from a Gaussian integer. But what we are going to do is something slightly different. Rather than prove it geometrically, which tells us that this here is always true, for some Gaussian integer, we are going to do a more constructive proof that will allow us to determine how to find Q from the given A and B. And so our proof will be stronger in that regard, but more involved and technical as a consequence. But I highly encourage you all to also consider the geometric argument by thinking about the square and proving that, yes, there is a Gaussian integer whose modulus to the point z in question is root 2 over 2. And you actually don't need to restrict to the case where a and b are Gaussian integers, but rather if you have some arbitrary complex number. So let's go ahead and prove this. So the first thing we are going to do is to establish notation. So we're going to let a and b be Gaussian integers of the following forms. We're going to have a be L plus Si, and we're going to let b be U plus Wi. And here we have that L, S, U, and W are integers. And now we are going to consider the ratio 0 equals A over B. And so this here is what we are defining to be z. So we consider the ratio A over B, and then this is going to be L plus Si over U plus Wi. And if we continue through algebra, what we are going to get is the following. So multiplying by the conjugate of a U plus Wi, that is going to result in U minus Wi in the numerator over U minus Wi. And so going ahead and expanding, the denominator is the difference of squares, so we rationalize this. So now we have U squared plus W squared. In the numerator, upon simplifying, we're going to have LU plus SW plus I times SU minus LW. And so we can go ahead, write this down as the real part of Z plus the imaginary part of Z. And now what we are going to do is let A1 be LU plus SW, let B1 be SU minus LW, and let T be U squared plus W squared. And so that is summarized here. So we have the following quantities. And now what we are going to do is apply the division theorem. So by the division theorem, so actually before that, just a quick observation. So note that by construction, A1, B1, and T, these are all integers by their definition. So we are fine here. So we can apply the division theorem. So applying the division theorem, and the proof of lemma 1.16.4, which I'm going to go to in just a moment, we get that there exists integers q1 and r1 in Z such that we have the following. A1 is equal to q1t plus r1, so that's just applying the division theorem. But where lemma 1.16.4 comes in is that it tells us that we can choose r1 to be less than or equal to t over 2. And so we have this here. And so let me go ahead and remind you of the proof of lemma 1.16.4. So as part of our proof of Euler's descent lemma, we showed that we can take our remainders, r and s, to be less than p over 2. And in this case, we had it was strictly less than because we are assuming that p is odd. So we had this condition here that this was a strictly less than. But now this same idea and argument allow us to say that we can go at most t over 2 since t could be even. And so we may have that be a possibility. But now, the inequality that we have that the absolute value of R1 is less than or equal to t over 2, this gives the following. That the absolute value of R1 over t is at most 1/2. Now we're going to go and consider A1 equals Q1t plus R1, and what we are going to do is divide everything by t. So next, divide by t in the first equation to get A1 over t equals Q1t over t, but I'm going to go ahead and skip a step and just bring the Q1 over, since Q1t over t is just going to be Q1, and this is going to be equal to R1 over t. And as a consequence, we get that the absolute value of A1 over t minus Q1 is going to be at most 1/2. So we have this condition right here. If we do the same argument for B, we are going to get the following. So similarly, similar argument. Gives that there exists Q2, R2 in the integers such that B1 is equal to Q2t plus R2 with absolute value of R2 being less than or equal to t over 2, and the absolute value of B1 over t minus Q2 being less than or equal to 1/2. So we have both of these here. And now, this is the benefit of this proof versus the argument that I mentioned geometrically that we know from the fact that the shortest distance to any point in a square to a vertex is root 2 over 2. Here we are actually going to be able to construct the Gaussian integer q, and it's going to be the following quantity. We're going to let q be just q1 plus q2i. So now set q to be equal to q1 plus q2i. And what we want to show is that z minus q is going to be at most root 2 over 2. So then we have z minus q, which is going to be equal to, inside we're going to have a over b, and then we have q1 plus q2i, so minus q1 minus q2i, and so we have this here. But we established that a over b by definition is going to be a1 over t plus b1 over t times I. So this here is the same. In terms of the real part, we're going to have a1 over t for the real part of a over b minus q1. And then the imaginary part is going to be I times the imaginary part of a over b, which is b1 b1 over t minus q2. And so we're taking the modulus of this. But now the modulus of this is going to be the square root of a1 over t minus q1 quantity squared plus b1 over t minus q2 quantity squared. So we have this here. But we already know that these here are both at most 1/2. And so here's where the inequality comes in. So we know that this is going to be at most 1/2 quantity squared plus 1/2 quantity squared, which is going to be equal to root 2 over 2 upon simplifying. And we are now done. We have now shown constructively how to find the Gaussian integer, since the division theorem via the Euclidean algorithm allows us to construct a Q1R1. And so we now have a way of determining that value. Alternatively, we can also argue how to find the Gaussian integer, and there's many ways of doing this. You could also argue that if you have a complex point z, you can take the floor function of the real and imaginary parts and then find where that value would be in terms of the square, and then determine what is the the vertex that's closest to it via that argument. And so that will also give another proof of this lemma. So let us now go ahead and prove the division theorem for the Gaussian integers. And so the statement is that if we have Gaussian integers a and b with b not equal to 0, then we can find Gaussian integers q and r, such that a is equal to q times b plus r, and we have that the norm of r is less than the norm of b. So here's the proof. So we have the following. So we're going to go ahead and let z equal a over b. So by lemma, the lemma we just proved, we know that there exists some Gaussian integer such that the norm, the modulus of z minus q is at most root 2 over 2. So we have this here. Now we're going to go ahead and define r in terms of a, b, and the Gaussian integer. So specifically, let r be equal to a minus this q that we just constructed times b. So we have this quantity right here. And so that right there is telling us that a is equal to qb plus r. And so that's the idea here. So we have this part here being satisfied. So now what we need to show is that the norm of r is less than the norm of b. And that's what we are going to do next. So we're taking the modulus of r, and if we can show that the modulus of r is strictly less than the modulus of b, that will in turn imply that the norm of r is less than the norm of b. And so we have modulus of r is equal to the modulus of a minus qb. Now we're going to go ahead and do the following. This is the same as a times b over b. So we're just multiplying by 1 cleverly. Minus qb. Next thing we're going to do, because now we have a over b, that's the same as z times b minus qb. We can factor a b out, and now we have modulus of b, and then modulus of z minus q. But we know that the modulus of q is at most root 2 over 2, so we know that this here is going to be modulus of b times root 2 over 2, which is less than the modulus of b. Since radical 2 over 2 is at most 0.7. So we have this here. And now, as a consequence, we have that the norm of R is less than the norm of B, since the modulus of some quantity x, of some Gaussian integer x, squared is equal to the norm of x. And so that finishes it off for this proof. And so we have established now the division theorem for the Gaussian integers. But now, what you want to note is that because Q can be constructed via the previous lemma, this is now a constructive proof, because we know how to find Q based on lemma 1.21.1. Specifically, we want Q to be built from the division theorem over the integers. And that's what we did exactly over here. We had Q2 in R2, and we let Q be Q1 plus Q2i. And so we know how to find Q, and so therefore we can find R based on that Q that the previous lemma constructs. So we're going to move forward and now talk about greatest common divisors. As I mentioned at the beginning of the video, over the Gaussian integers, we no longer have a unique greatest common divisor, but rather a greatest common divisor. So given Gaussian integers a and b, with at least one of them being non-zero, a greatest common divisor of a and b is a non-zero element in the Gaussian integers, which we're going to be calling d, which satisfies the following two conditions. D divides a and d divides b, and if f is in the Gaussian integers with f dividing a and f dividing b, then f will divide d. And we will go ahead and still use the same notation. We're going to denote the GCD of a comma b by just GCD of ab. But just keep in mind that this is not a unique quantity. And that's just the main aspect as we continue, is that the GCD is going to be unique up to unit. And so if we have a GCD, it will differ from any other greatest common divisor by a multiple of a unit. But now we can go ahead and prove Bézout's lemma for the Gaussian integers. So we're going to choose a and b to be Gaussian integers with at least one of them being non-zero. And we're going to let d be the GCD of a and b. And the claim is that we can find Gaussian integers x and y such that ax plus by is equal to d. So before we start this proof, I'm going to go ahead and revisit the original proof that we did for Bézout's lemma at the start of the term. So here's the proof. In our case, for the Gaussian integers, we are considering the case where both a and b are not identically zero, so we're in the setting of case 2, where one of a or b is non-zero. And so the way the proof went was by constructing this set S of a comma b, where we're looking at all the linear combinations of an plus bm, which had the property that they were greater than 0. So, and then we had this was a subset of the naturals, and we went through our argument via the wall ordering principle. We are going to do the same exact argument. The only difference is, instead of considering this as a quantity over this, if we consider an plus bm, where now a and b are Gaussian integers, then we cannot apply the wall ordering principle. So instead, we're going to be taking the set of the norms of w, where w is equal to an plus bm. And once we have that, you'll see that the proof that we are about to do is almost verbatim the proof we did earlier. And to emphasize this, I'm going to go ahead and copy this proof, and we're just going to make the edits as we need throughout the argument. So here's the original proof for Bézout's lemma. And now what we are going to do is follow in the footsteps of Emmy Noether and many mathematicians that came after, and realize that these arguments that we have for the integers that already existed, if we are careful, we can extend the same arguments to more general settings. And so we're going to be doing this in the case of the Gaussian integers. But if you take abstract algebra, you will actually see this result in a more general setting for commutative, what are known as commutative rings. And so let's go ahead and see this. So we're going to go line by line, make the necessary adjustments so that this proof continues to hold. So first line is fine. Suppose one of A or B is non-zero. That's our assumption. Then define S of A comma B to be the set given there. Now we are in trouble here because of course we don't have an ordering over the Gaussian integer, so this greater than 0 doesn't work. So that's the first adjustment we need. So we're going to go ahead and let S of A comma B be the set consisting of the norms of W such that W is equal to NA plus MB for some for N and M Gaussian integers. But we had in the original set that 0 was removed. And so what we are going to do now is remove 0 from this. And so as a consequence, this is a subset of the natural numbers. And so we have our set here. Oops. And so this is the set that we're looking for, our S of A comma B. So moving on to the next line. With all loss of generality, suppose that A is not equal to 0. Then A or negative A is in our set S of A comma B. Well, now we have to be careful because that's not true. Just because A is non-zero, A is now a Gaussian integer. So A may not even be in here because this is a subset of natural numbers. And so what we need to do is make an adjustment. And so the way we're going to adjust this is because if A is non-zero, we can take M to be 0 and we can take N to be 1. So we have that the norm of A is in this set. And so that's the idea here, is that the norm of A is in the set S of A comma B. And so as a consequence, we have that the set is non-empty. So by the Wolverine principle, we know that there is a least element, which we called U in the original proof. But now we're going to switch things around because originally we wanted our U as an integer so that we had this here. So now we want there to exist the least element to be in terms of norms, since this is going to be in terms of the norm of something. And so we're going to have that there exists some U in the Gaussian integers such that the norm of U is in SA comma B is the least element. So let's go ahead and write that down. And so this is what we have now. We have that there exists some Gaussian integer U such that the norm of U is the least element in S of A comma B. Then the next part of the proof is that there exists X and Y in the integers, but now we want them to be Gaussian integers. So we have Z adjoin I such that U is equal to AX plus BY. And now we want to take into account the greatest common divisor. So we know by assumption that D is the greatest common divisor of A and B. So we have that D divides A, D divides B, and so linear combination lemma, which we established for the Gaussian integers, tells us that D divides U. But now we need to change things slightly. We no longer have an equality. But what we do have is that the norm of D is less than or equal to the norm of U. And so we do have this statement here. The next statement is that it suffices to show that U is less than or equal to D. And while our first instinct to translate this is norm of U is less than or equal to norm of D, since that is in line with what we just did earlier, we do have to be careful. Because if we have that the norm of U is less than or equal to the norm of D, that does show that the norms are equal. But we showed in our last lesson that 2 plus I and 2 minus I are both relatively prime. But while they are relatively prime, they have the same norm. And so we just can't say that to show U is less than or equal to D, that's enough. And so what we are going to do is replace that less than or equal to with divides. And so we want to show that u divides d. And so now we apply the division theorem to u and r. And what we have, and so I just noticed that this is a u and that's an r, so I apologize for the handwriting. And so we have, by the division theorem for the Gaussian integers, that we can find Gaussian integers q and r such that a is equal to u times q plus r. But now, of course, we have the inequality being replaced in terms of norms. And so we have norm of r is less than norm of u. Now we go ahead and write r as equal to a minus u times q. Go about the same expansion we did back in the original proof of Bezo's lemma, and all of this continues to hold. And now what we have is that if the norm of r is greater than 0, we are going to have that r is going to be in here. And so that's the key change, is that now we want to replace this statement here with norm of r. But now norm of r being greater than 0, r is a Gaussian integer, so we need that to be the norm of r. So we have norm of r is in this set S of a comma b. But now we are in trouble, because this here is in here. We know that the norm of r is less than norm of u, but the norm of u, by construction, is the least element of S of a comma b. And so that's what we had up here. And so norm of u is the least element. And so this contradicts the minimality of u, but specifically the norm of u in S of a comma b. And therefore the norm of r is equal to 0. But if the norm of r is equal to 0, then r is equal to 0. So now go ahead and write this right above it. So we have to put in this extra line, that then r is equal to 0. And so if r is equal to 0, that tells us that a is equal to u times q. And so now we have that a is equal to u times q. If we do the same exact argument of applying the division theorem to b and u, we're going to get that b is equal to u times q prime plus r prime for some q prime r prime in the Gaussian integers. And then of course we have to replace that the inequality appearing over here is all in terms of norms. So let me go ahead and do that. And so here we have it, q prime are Gaussian integers. Norm of r prime less than norm of u. The same argument we just did, just right above, in the case of the division theorem applied to u and r, will give us that b is equal to u times q prime. But if b is equal to u times q prime, then we have that a is equal to u times q, b is equal to u times q prime, and that will tell us that then u divides d. And now finally, this does not tell us that that u is less than or equal to d, but it tells us that u and d differ by a unit. And so what we have here is that thus there exists a v, there exists a unit v in the Gaussian integers such that u times v is equal to d. And here we're using this result from last time, that if r divides s and s divides r, then we know that there is some unit in the Gaussian integers such that r is equal to u times s. Now to finish off the proof, so finally, we have that U is equal to NA plus MB for some, UX plus YB, and so that's from, where are you? Right here. So we have this statement. So we know U is equal to AX plus BY. Now we multiply both sides by V, and we get D is equal to U, V, which is equal to A, and then we have X times V plus B, and then we have Y times B. And so we have that this is here, these here are our desired X and Y. And so now that concludes Bezo's lemma. But notice that once we put it in this way, what we really see is that we have just gone ahead and made revisions where necessary to the argument. But morally, this is the same argument we gave at the beginning of the term, just adjusted for the Gaussian integers. So the next statement we're going to show is that if A and B are Gaussian integers with at least one of them being non-zero, and D is the GCD of A and B, then we have that for U a unit in the Gaussian integers, then U times D is also a greatest common divisor for A and B. So here's the proof. So by definition, we have that there exists Gaussian integers x and y such that A is equal to x times D and B is equal to y times D. Now let's go ahead and let U be a unit in the Gaussian integers. Then we have that its multiplicative inverse is also a Gaussian integer. And so we have this here. And now what we are going to do is the following nice clever trick. So then we have that A is equal to x times U, x times U inverse times U times D. And so here we're using the fact that U inverse times U is equal to 1. And similarly, we have that B is equal to Y times U inverse times U times D. And so we have this here. And so thus, we have that UD divides A and U times D divides B. So we have established this part of the definition for U times D. And so now what we want to take is that if we take some quantity f in the Gaussian integers with f divides A and f divides B, we want to show that that divides U times D. So next, let f be a Gaussian integer with f dividing A and f dividing B. So we have this here. Then, because D is a greatest common divisor for A and B, we have that f divides D, and as a consequence, we have that f divides U times D. And hence, we have that UD is a greatest common divisor. And so this shows us that the moment we have one GCD, we actually have that a unit times that quantity is also a GCD. But this leaves the door open. How many GCDs are there? Because now we have found that we have one, we can find others from it. And that's with the context of the next question, which tells us how to establish uniqueness of units. Uniqueness of greatest common divisors up to unit. And so now let's go ahead and show that uniqueness of greatest common divisors up to unit. So here's the statement. If a and b are Gaussian integers with at least one of them being non-zero, and d is the GCD of a and b, and we have that f divides a, f divides b, then the norm of f is less than or equal to the norm of d. And if the norm of d is equal to the norm of f, then we have that d is equal to u, a unit u times our quantity f. And so that will establish that we have uniqueness of greatest common divisor up to unit. Because what we are looking at is anytime that we have a divisor f, such that f divides a and f divides b, that has to divide the greatest common divisor. But if the norm of f is always less than or equal to the norm of d, then we have by the multiplicativity of, what we will show is by the multiplicativity of the norm of f will have to equal, if norm of f is equal to norm of d, then f is equal to a unit times d. So let's go ahead and prove this. So here is the argument. So we're going to apply Bezo's lemma. So by Bezo's lemma, there exist Gaussian integers x and y such that we have that ax plus by is equal to d. By the linear combination lemma, which we have for the Gaussian integers, we have that that f divides d, since f divides a and f divides b by assumption. In particular, there exists some u in the Gaussian integers such that f times u is equal to d. Now we take norms. Will yield the following: that the norm of f times the norm of u is equal to the norm of d. But now these are natural numbers. So consequently, we have that the norm of f is always going to be less than or equal to the norm of d. And so moreover, if norm of f is equal to the norm of d, then the norm of u is equal to 1, which implies that u is a unit. And that's what we wanted to show. So now we are done with the whole proof. Because we know that f times u is equal to d, and that's what we have over here. And so we have finished the proof of the lemma. In the same way that we have a Euclidean algorithm for the integers, we also have one for the Gaussian integers. And what it tells us is that if we have Gaussian integers a and b, if we apply the division theorem and divide a by b, we're going to have a is equal to b times q1 plus r1, norm of r1 less than norm of b. And if r1 is not equal to 0, we can apply the division theorem once more and get b is equal to r1 times q2 plus r2. And now we have a descending sequence of natural numbers. Well, natural numbers along with union 0. And so we can continue in this manner until we get a remainder of 0. So we can go ahead, same as before, as we did for the integers, and continue until we get a 0 for the remainder. And that's essentially the Euclidean algorithm for the Gaussian integers. And you'll have some examples in the homework to experience this. The following lemma, and then the proof of the algorithm revolves around the proofs of the following lemma. And so specifically we have a, b, q, and r. These are integers. A is equal to b times q plus r. And the GCD of a and b, then the GCD of a and b is equal to a unit times the GCD of b times r. So this will be part of your homework. And as a consequence of the lemma, you will show the existence of greatest common divisors in the Gaussian integers. And so if we have Gaussian integers a and b, through the Gaussian integers, through the Euclidean algorithm, we have that the last term r sub n is going to be the GCD of a and b. And so this will be one of the homework questions that you'll see. And now this demonstrates that these notions that we have for the integers, they continue to just extend over to the Gaussian integers, and that will provide us in our next lesson with being able to prove a fundamental theorem of arithmetic for the Gaussian integers. To finish it off for today's lesson, let us go ahead and show the necessary and sufficient conditions for finding a solution to a linear Diophantine equation over the Gaussian integers. And it's exactly what we had over the integers, just translated over, as has been the theme for today. We have a, b, and d, Gaussian integers, with at least one of a or b being non-zero. The equation ax plus by equals n has a solution in the Gaussian integers if and only if the GCD of a and b divides n. So let's prove this. So to make things simpler, let's go ahead and let d be the GCD of a and b. And so now let's consider the forward direction. So here we have that there is a solution to the linear Diophantine equation. So let x and y be Gaussian integers such that ax plus by equals n. By definition, we have that d divides a and d divides b. So by the linear combination lemma, then implies that d divides n. And that tells us the first part of the statement. So let's go ahead and do the converse. So now we have that the GCD divides n. So we're going to apply Bezo's lemma. So by Bezo's lemma, for the Gaussian integers, we know that there are x and y such that ax plus by is equal to d. But if we go ahead and multiply, since d divides n, so jumping ahead, since d divides n, we know that there exists some Gaussian integer f such that d times f is equal to n. So now if we multiply the equation we have, we get the following. So we're going to go ahead and multiply by f. We have a fx plus b yf is equal to d times f, which is equal to n. And therefore, fx comma yf is a solution to the linear Diophantine equation ax plus by equals n. And so we're done. And so that establishes the proof. And in our next lesson, we'll go ahead and continue this and prove Euclid's lemma and build towards the fundamental theorem of arithmetic for the Gaussian integers.